Okay, so we're going to try to sketch the graph of this function here, and I encourage you to maybe pause the video and try to sketch it yourself to begin, or maybe pause it and go through each step, like finding the domain and then pressing play, then finding intercepts, then pressing play, etc. Something like that. At very least, do at least write everything down along with me so that you get the solution to this problem of sketching the graph of this function in your notes. All right, so the first thing that we always like to do is put up a large set of axes right at the top of our page so that we can put our information on as we go along. So let's draw a big set of axes here. Okay, something like this. Okay, so here's our x-axis, and here is our y-axis. And the next thing that we like to think about is domain. That's an easy thing to think about. So A, what's the domain of this function? Right, so the domain of this function f, it's equal to, well, let me just write down what our function is again. I'll probably have to keep doing this, unfortunately. Here's f of x over here. F of x is equal to 9 times x minus 1 times x plus 3 over x minus 3 all squared. Alright, so the domain of this function is wherever it makes sense, which is to say wherever we're not dividing by 0. We'll divide by 0 only when x minus 3 is 0, which is to say when x is 3. So the domain of this function is set of all x, so it's equal to the set of all x such that x is not equal to 3. Okay, so the only point not in the domain of this function is 3, so let's just mark that on our graph. So let's put it, say, around here. So at 3, x equal to 3, our function isn't defined. 3 isn't in the domain. So later on, when we're looking for vertical asymptotes, if they're going to appear anywhere, they're going to appear in places where our function is not defined. So the only real possibility where we might have a vertical asymptote is at x equals 3. Keep that in mind for the future. All right. So the next thing we like to think about is symmetry. So B, symmetry. So in particular, certainly not periodic, so we might ask if f is even or odd. F, remember, is even. If f at minus x is equal to f of x, and it's odd if f at minus x is minus f of x. So we're looking to see if f at minus x is equal to plus or minus f of x. That's our question here. And if you want to check this, what do you do? Well, you just evaluate f at minus x by replacing all occurrences of x in the formula for f by minus x, and you see what you get. And this is going to look, in this case, like 9 times minus x minus 1 times minus x plus 3 all over minus x minus 3 all squared. And if you At this point, what you should do is you should try to make this right here look like either f of x exactly or like the negative of f of x. And you can try and do that maybe by pulling out this negative here, but what you'll find is that whatever you do, you won't see either f of x or minus f of x. So we can write that this actually is not equal to plus or minus f of x, so that means there's no symmetry. Okay, so there's no symmetry, so we don't, so this function is, the graph of this function is not going to look either the same on either side of the y-axis as it would if it were even, or opposite on either side of the y-axis as it would if it were odd. All right, so next thing we want to think about is C. We usually look for intercepts. That's an easy thing to do. All right, so we'll look for intercepts. All right, so first thing we'll look for are y-intercepts. Y-intercepts, okay, so when do we have a y-intercept? That's when we cross the y-axis. So when we cross the y-axis, x is 0, so we just solve for y equal to f at 0. All right, so let's see what we get. F at 0, in this case, is equal to, so we just replace our x in the formula for f by 0, and we'll get here 9 times 0 minus 1, which is minus 1, times 0 plus 3, which is just 3, divided by 0 minus 3 squared, which is, minus 3 squared, not cubed. Which is 9, canceling the 9s, we end up with minus 3. Okay, so our y-intercept is going to happen at minus 3. So let's put that on the graph right now. So we'll put that on our graph. So at minus 3, we're going to cross the x-axis. All right. All right. Maybe I should make that one yellow too. All right. So at minus 3, rather, we're going to cross the y-axis. That is our y-intercept. All right. So now we want the x-intercepts. Well, when do we have x-intercepts? X-intercepts happen when y is equal to 0. So we'll just set y equal to 0 and solve for x. All right. So x-intercepts. So we're looking for when f of x is equal to 0. So, well, what is f of x? F of x is equal to, looking at the formula, 9 times x minus 1 times x plus 3 divided by x minus 3 all squared. So we're wondering, when is this going to take the value 0? And that's going to happen when the numerator is 0. And the only time that the numerator gets to be 0 is when this factor is 0, which is to say when x is 1 or x is minus 3. So if and only if x equals 1 or x equals minus 3. All right, so our x-intercepts are at x equal to 1 and x equal to minus 3. Let's put those x-intercepts on the graph of our function. So here we are. So what were they again? They were 1 and minus 3. So let's see. So here's 1. at x equal to 1, we're going to have an x-intercept, and at x equal to minus 3, which I guess is somewhere like that, we'll also have an intercept. So I'll put a 1 here, and I will put a minus 3 right here. Okay, so this tells us at least a little something about the graph of this function already. We're going to cross the x-axis here, and we're going to cross the y-axis here, cross the x-axis here, and it's not going to exist here. All right, so that's some information which is helpful. All right, so let's continue. Okay, so the next thing we like to think about are asymptotes. So we do all these first things without having to do any calculus. So asymptotes. So first of all, we'll look for horizontal asymptotes, which is to say, we'll ask, what does our function look like as x tends to plus or minus infinity? Right, so we want to know, what does f of x look like for really large positive values of x and large negative values of x? So here we are. So the limit as x tends to infinity first of f of x is equal to the limit as x tends to infinity. Here's our formula for f of x. It's 9 times x minus 1 times x plus 3. It's x minus 3 all squared. All right, we're taking a limit at infinity. So remember that what we do is we just drop all lower powers of x in the numerator. What's the highest power of x that we're going to get in the numerator? It's going to be when we multiply these two highest powers of x here, and we'll end up with 9 times x squared. So in the numerator we'll have 9x squared. And in the denominator, our highest power of x is again going to be x squared, dropping lower powers of x in the denominator. All right, now what's this? This is the limit as x tends to infinity of 9. And as x gets big, 9 means that it's 9. All right, so as x tends to infinity, f of x tends to 9. And also, if we were to take the limit as x tends to minus infinity of f of x, well, what would we do? We take the limit as x tends to minus infinity, same thing. Dropping lower powers, we'd have this, and canceling, we'd have this, and the limit as x tends to minus infinity of 9 is again 9, so we can just write down that this one's going to be 9 as well. All right, so what can we say? We can say that the line y equal to 9 is a horizontal asymptote of y equals f of x. All right, so let's put that on our graph right now. Okay, so we have that y equal to 9 is a horizontal asymptote. I don't have to do things completely to scale. If I were to do it to scale, there's 3, 6, 9. Oh, maybe I can get away with that. All right. So here's our y equal to 9. And that's our horizontal asymptote. So as x tends to infinity, f of x is approaching 9, and as x tends to minus infinity, f of x is also approaching 9. So it looks something like this, like this, like this, like this. Who knows, maybe I'm crossing that. I can cross that horizontal asymptote. We'll find out very soon. All right, next thing we want to do is we want to look for vertical asymptotes. And remember, if we're going to have a vertical asymptote, it's most likely going to, if it's going to occur anywhere, it's going to occur at a place where our function doesn't exist. It's going to occur at a point not in the domain. The only point that we have not in the domain is 3. So we'll just check to see if x equal to 3 is a vertical asymptote. We'll do that now. Alright, so vertical asymptotes. So what are we looking for? We're looking for those A, if they exist, they might not, where as x tends to A from either the right or the left, f of x tends to plus or minus infinity. Alright, so that's what we do now. So, as I just said, as 3 is not in the domain of f, we should check x equal to 3. So to do that, what do we need to do? Well, we need to take the limit as x tends to 3 from both the right and the left of f of x and see what happens. So we're taking the limit as x tends to 3, let's say first from the right, of f of x. That's the limit as x tends to 3 from the right of, what was our function again? There it is, 9 times x minus 1 times x plus 3 all over x minus 3 all squared. And what's happening here, well, as x tends to 3, the numerator is going to tend to, I guess it's going to tend to 9 times 3 minus 1, which is 2, times 3 plus 3, which is 6, so it's 9 times 12, I guess that's 108. So the numerator is tending to 108, and the denominator is tending to, well, as x gets close to 3, x minus 3 gets close to 3 minus 3, which is 0. And in fact, whether we're approaching 3 from the right or the left, so whether or not x minus 3 is positive or negative, when I square it, I'm going to end up with a positive value. So, in fact, this is tending to 0, and it's tending to 0 from the right. In fact, in both the case when x tends to 3 from the right or the left. So in fact, we'll get the same limit when we approach 3 from the left. For now, just writing down the limit as x tends to 3 from the right, what will we get? For all x's we're considering, we're going to have a numerator close to 108 divided by a very small positive value. It's going to be very big. This is tending to plus infinity, and similarly, for exactly the same reason, the limit as x tends to 3 from the left of f of x is equal to infinity 2. Alright, so let's put this on. What do we have? We definitely have now that x equal to 3 is a vertical asymptote, because as x tends to 3 from either the left or the right, f of x tends to infinity. Okay, so we got to go all the way up here. There we are. And what do we have now? We have that at x equal to 3, we're going to have a vertical asymptote, and as we tend to 3 from either side, in fact, we're tending to plus infinity, so let's put that on. Let me see, what color should our graph be? Let's make it blue. Okay, so like that, and like that. my room, I would change things. Let me just think I better do a better job of this one for later. It's going to look like something like this. Just leave it like that for now. All right. Okay, so now we have a bit of information. Okay, so we got quite a bit of information without doing any calculus. We're going to have a horizontal asymptote at y equal to 9. And then it seems like we're going to have to cross. So this is just guesswork. We don't really know until we do calculus whether we're always going to be decreasing here or not. But it seems like we're going to do something like this. Come down. Like this, cross the x-axis, cross the y-axis, cross the x-axis, then somehow I've got to get up towards infinity. I've got to have a vertical asymptote here as well. So from infinity, and then somehow I've got to get to this horizontal asymptote. Maybe I come down and then go up like this. We don't know until we do some calculus, until we know exactly when f is increasing and decreasing, and we'll also want to know about the concavity of f. So let's do that now. Right. Okay, so where are we at? That was D. I guess we're at E. All right, so E. Looking for where a function is increasing and decreasing. And usually at this point we look for CNs, critical numbers. All right, and if we're looking for where f is increasing and decreasing, well, all we're doing is we're looking for the sign diagram of f prime. Because the sign diagram of f prime is going to tell us where f prime is positive and negative, and we know that when f prime is positive, f is increasing, and when f prime is negative, f is decreasing. All right, so if you're looking for the sign diagram of the function, what do? You look for where it's 0 and where it's discontinuous, which is to say for our functions where it doesn't exist. So what was f prime of x? Well, we were given f prime of x way back in the beginning, and here it is. It was minus 72x. If you want to scroll to the top, you'll see it. Probably had enough of me scrolling to the top, so I'll skip that. And minus 72x, I have it here, divided by x minus 3 all squared. We're looking for where this is 0 and where it doesn't exist. This is 0 exactly when the numerator is 0, and that's going to happen when x is 0. Because 0 is in the domain of f, that means 0 is a critical number. All right, so 0 is a critical number. All right, and let's note that f at 0, well, we actually already calculated that. F at 0 was minus 3. Okay, so at x equal to 0, y equal to minus 3, we have f prime of x equal to 0. That means we're going to have a horizontal tangent line. We'd better put that on the graph of our function, so let's hike all the way to the top. Maybe I'll pause it and then get there. Okay, so at x equal to minus 3, we're going to have a horizontal tangent line. So let's put that on right now. So at x equal to 0, rather, y equal to minus 3, we're going to have a horizontal tangent line. So I'll indicate that here. All right, so now let's continue back down and see what we got. So continuing with the sign diagram of f prime, we found out where f prime of x was 0. That was when x was 0, and we want to know when is f prime of x equal. When does f prime of x not exist? F prime of x does not exist exactly when x is equal to 3. This isn't going to be a critical number because x equal to 3 isn't in the domain of f. The critical numbers are those numbers in the domain of f, where the derivative is 0 and where the derivative doesn't exist, but because 3 isn't in the domain, this isn't a critical number. Let's just write down that this is in fact a vertical asymptote. Nonetheless, when looking for the sign diagram for f prime, what do we want? We want to put on all those places where f prime is 0 and where it doesn't exist. We just saw that it's 0 at 0, and it doesn't exist. So put a round circle there at 3. This was a vertical asymptote. This was a critical number. Just note that. Now, for the sign diagram for f prime, what do we do? Well, we know that because we put all points where f prime is 0 and where it's discontinuous, which is to say where it doesn't exist, know that f prime can't change sign on any of the intervals determined by the numbers 0 and 3. So, to check the sign of f prime on any one of these intervals, we just have to evaluate f prime at one number in these intervals. So, for example, what if we calculated f prime at minus 1? Well, what would we get? We get negative times x at minus 1 is negative, which is positive, over a negative squared, which is positive. We'd actually get something which... Do I have the derivative written down correctly? Let me pause for one moment. No, you probably noticed this and have been very concerned, but not to worry, I notice now. F prime of x is actually minus 72x over x minus 3 all cubed. Alright, everything else is fine to this point. F prime, though, at minus 1 is actually going to be negative times negative is positive over a negative, which is negative. So it's going to be less than 0. Alright, so that means on the entire interval, f prime is going to be negative. And you can check to see that on the interval 0, 3, it's positive, for example, by evaluating f prime at 1. And on the interval 3 to infinity, it's negative, for example, by evaluating f prime at 4. I'll let you check that. Note, in this case, f prime is changing from negative to negative, but that doesn't always necessarily happen. Just because this one is negative doesn't mean that we have to alternate in sign on the following intervals. So do be careful about that. Okay, well, what does this tell us? I now know that f prime is negative on the interval minus infinity to 0. That means that f is decreasing on this interval. So we can do that. So f is decreasing on that interval. On the interval 0 to 3, f prime is positive. That means f is increasing on this interval. And on the interval 3 to infinity, f prime is negative, which means that f is decreasing on this interval. Alright, so that finishes the sign diagram for f prime. We now know where f is increasing and decreasing. Now, let's continue on, and we're interested in knowing where f has a local max and a local min. I guess we should probably write in words. This is a good idea. F is actually increasing on the interval 0, 3, and it's decreasing on the interval minus infinity to 0, union with 3 to infinity. And now the next thing that we like to talk about are local max and min. Grad f. So local max and min. And for this, all we have to do is look at the sign diagram that we just constructed for f prime. We see that f is decreasing towards 0 and increasing to the right of 0, that means that f is definitely going to have a local min at 0. By the first derivative test, because 0 is in the domain of f, 0 is a critical number of f. F, you'll note, is also increasing to the right of 3. Rather, it's increasing to the left of 3 and decreasing to the right of 3, but in this case, because we have a vertical asymptote at 3, because 3 isn't in the domain of f, we can't say that f has a local max at 3. So we just can say that f has a local min rather, at 0. So by the first derivative test, we can say that f has a local min at x equal to 0, and in fact we already calculated and we noted that f at 0 is minus 3. Alright, so now the last thing that we want to consider is concavity. That looks like G. Okay, so G, concavity. And inflection points. If we want to know the concavity of f, all we have to do is construct a sign diagram for f prime prime. When f prime prime of x is bigger than 0, we'll know that f is concave up, and when f prime prime is less than 0, we'll know that f is concave down. If we have a sign diagram for f prime prime, we'll know exactly when f prime prime is bigger than 0 and less than 0. Okay, so for the sign diagram, as with any sign diagram, we just look for where our function is 0 and where it's discontinuous, which is for us to say where it doesn't exist. So f prime prime of x, we wrote that one down at the top as well, we were given it, was 72 times 2x plus 3 divided by x minus 3 all to the fourth. And we're looking for where this is 0 and where it doesn't exist. It's 0 exactly when the numerator is 0, which is going to happen when 2x plus 3 is 0, which is to say when x is equal to minus 3 halves. So if x is equal to minus 3 halves, and it does not exist, exactly when the denominator is 0, which is going to happen when x minus 3 is 0, which is to say when x is equal to 3. Alright, and let's note again that 3 isn't in the domain of this function. X equal to 3 is a vertical asymptote, so a vertical asymptote. Alright, so this is all we need for our sign diagram for f prime prime. F prime prime was, it didn't exist at 3. That was our vertical asymptote. And it was 0 at minus 3 halves. So put a solid circle there, and minus 3 halves. I'll let you check the sign of f prime prime on each of these intervals. Remember, can't change sign on any of these intervals, so you just have to check at one point in each interval. For example, if you evaluated f prime prime at minus 4, you would discover that you'd get a negative value. So in the entire interval, minus infinity to minus 3 halves, it's negative, and then it's positive. And then, in fact, it's positive. Again, what does that tell us about f? Well, if f prime prime is negative, f is concave down. If f prime prime is positive, f is concave up. And if f prime prime is positive again, f is concave up. What do we notice? Well, we notice that f, the concavity of f is going to change sign on either side of minus 3 halves. So, at minus 3 halves, we're going to have an inflection point, and this is going to be our only inflection point. So, we're going to have an inflection point at minus 3 halves. Let's write down that minus 3 halves, comma, f of minus 3 halves. So our inflection point is always an actual point on the graph. It's the point minus 3 halves, f of minus 3 halves. That, you can check, is minus 3 halves. Substituting minus 3 halves in for x in our original equation for f, you can check that's going to be minus 5/3. That's going to be an inflection point, so let's put that on the graph of our function, and then afterwards we can actually complete our sketch. So minus 3 halves minus 5/3, there we're going to change sign beside there will change from being concave down to concave up. So let's go up and put this point. One thing I forgot to write is NIP. Alright, so heading up to the top now. Right, so as we said, the point minus 3 halves, so for minus 3 halves, it should be right there, halfway between minus 3 and the y-axis, and minus 5/3, which is, well, a little more than partway down, halfway down to minus 3, so right around here. This point right here, I guess I'll put it on with blue. We'll label it here is an inflection point, minus 3 halves, we said, and minus 5/3. Okay, so that is an inflection point. And if we now take a look at our what we obtained from our sign diagrams from f and sign diagrams from f prime and f prime prime, if you take a look at those now, you'll see that we are supposed to decrease. Our function is supposed to be decreasing all the way up to x equal to 0. So we're going to decrease all the way up to x equal to 0, and y equals 9 was a horizontal asymptote. Because we're always going to be decreasing, I'm not actually ever going to be above this horizontal asymptote. I'm always going to, in fact, stay below it, at least to the left of 0. Okay, so we're going to decrease all the way until we get to here, and if you recall as well, we're supposed to be concave down until we get to x equal to minus 3 halves, and then we're concave up ever after. Alright, so let me draw that. Okay, so we have the horizontal asymptote here, and I'm supposed to decrease all the way, and I'm supposed to be concave down. Concave down all the way, and I cross the x-axis. I cross the x-axis at minus 3. Here I continue. I'm supposed to be concave down. Oh, it looks like I almost made it concave up. Okay, so concave down to this point here. Alright, let's do this. Okay, looks like I'm concave down all the way to this point here. At this point, when x becomes larger than minus 3 halves, at that point I suddenly become concave up, but I'm supposed to continue to increase, I'm supposed to continue to decrease rather, and I'm going to have this horizontal tangent line here. Okay, so there we are. So I hope this looks like I was concave down all the way up to the point minus 3 halves, and then as x increased from minus 3 halves, I became concave up. And in fact, if you look down again at that sign diagram for f prime prime, we'll see that from here on in, I'm supposed to be concave up everywhere. But as x increases from from 0 up to 3, I'm supposed to increase all the way, and I'm supposed to increase all the way, and I'm supposed to be concave up with this vertical asymptote here. Oh, and I'm also supposed to cross the x-axis right here. I've got that same thing, so I'm going to draw something like this. Increasing and concave up. So let's see how this goes. Okay, so here we go. Increasing and concave up. And look, I'm going to cross the horizontal asymptote. That is perfectly reasonable. You're allowed to cross horizontal asymptotes. Now, looking again at those sign diagrams for f prime and f prime prime, you'll see that we're supposed to decrease for x bigger than 3, and we're supposed to be concave up again for x bigger than 3. So let's draw this so that we're decreasing for x bigger than 3 always, and concave up. So it's going to look like this here. So here's my vertical asymptote at 3, and I decrease all the way, right? I'm never going to drop below this horizontal asymptote, because if I did ever drop below, I'd have to come back up again, and my function wouldn't actually be decreasing if that were the case. Alright, so there we are. We're done. Took a little while, but it was well worth it. Look at this. This is something else. I think you will agree. Here it is. Let's just write down a label. This is the graph of the function 9 times x minus 1 times x plus 3, all divided by x minus 3 squared. That will be the longest video I make this year. This page here, draw a big set of axes, and that way, as we get information about our function, we can put it on as we go along. Alright, so here's my x-axis, and here's my y-axis.